Okay, hi everyone. I'm Songlin from Purdue University, and today I'm going to talk about my work, Escape with Yourself, Sound and Expressive Bidirectional Typing with Avoidance for Reachability Types. So this is a very long title, so where do we start? We start with the last two words. What are reachability types? So basically this kind of a type system where we want to reason about resources via variable names. Our goal is that we track the sharing of resources instead of restricting the sharing. And the goal is that we want to achieve better expressiveness in comparison to, for example, the statically safe fragment of Rust, which strictly enforces the shared XOR mutable principle. So for example, here in this counter function, we see that there are two closures, incur and deter. They act as methods. They too share the underlying mutable ref cell named C. So for all three of them, we annotate C in the type qualifier of their types. So that's what sharing is tracked in those cases, in functional impure cases. But then when incur and deter are returned out of this counter function, they escape. So we need to preserve tracking on such escaping data. So when the return pair is assigned to the new variable name called counter, we need to annotate the extracted incur and deter with a new type qualifier using the name of counter. And after we have tracking in places, it's time to make some profit and do some real reasoning. So here, in an on-demand manner, functions, each of them, they can choose to request disjoint parameters. When they choose to do so, they annotate that tiny little diamond symbol on the type as a type qualifier of their parameters. So each of them represents that the parameters there should be disjoint from one another. So in this way, a function combinator like parallel can request that their parameter sums are separate from one another. So this gives us static safety in terms of no data racing. So all these reachability typing stuff have been declaratively established in prior works. So in this work, what we want to do is that we want to build type checking algorithms in a sound and expressive manner towards such reachability types. So what are the challenges? Well, since in our approach, since in the design of the type system, variable names is so important, naturally, and we will know that when you are actually programming, names are not enough to track data. So there are two really important cases where we observe that names are not enough to preserve the tracking. First of all, there's the avoidance issue where, for example, in an inner scope, we defined a variable x, and the data we're returning from this inner scope is also should be qualified by this x. But then in the outer scope, since all names are EU-scoped, that name has to be avoided from the typing. That's the first case. And the second case is about polymorphism. For example, for an identity function where the parameter reachability is polymorphic, represented by that diamond symbol as well, and the result qualifier has to depend on the bound variable of z. But that the bound variable cannot appear in the result of the application and need replacing. So in the first part of this talk, we'll be focusing on the first challenge of avoidance. And before I go on, I should note that avoidance is not a problem that is unique to reachability types. It is commonly seen in any kind of dependently typed system without evaluation types. There are several examples of them. For example, there's bounded existential types, there's dependent object types, which is a foundational calculus of Scala, and also it's commonly seen in ML module. And this is an example extracted from some paper actually discussing ML module and signature avoidance. So in the really simple case, how do we do avoidance? Well, the idea is that, for example, if a variable y needs to reach x, and x went out of scope, and x is reaching some nameless resources, then we can just bypass x and replace the EU-scoped variable x with the upstream reachability, the diamond symbol, outright, so that y is now the new name for this distinct unnamed resource, which is good. But would this same replacement mechanism work on more intricate cases, for example, on escaping data types? Actually, no. So since the diamond symbol needs to mark distinct resources, for example, here in this example, we have a pair, and both components of this pair is referring to the same variable x. If we just do a naive replacement, replacing all occurrences of x with diamond symbols, then basically this type will be changed into the wrong meaning, meaning that both components are referring to distinct components. So this is not what we want. Then what can we do about them? Well, the correct way is designated in reachability types to do so is that we need to go through an indirection via something called self-references. So you may think of these self-references, named P here, as something similar to these pointers found in object-oriented programming. So this notion of P represents the whole pair. So instead of saying that both components are reaching some external variables, we say both components reach some resources that is enclosed within this pair itself. And this pair itself is reaching the unique diamond resources. So in this way, we preserve the invariant of those both components sharing the same data. So here comes our title. The core mechanism is that we track escaping data with self-references. That's the title pun is escaping with yourself. Okay. In this signature of the pair type, P represents the whole enclosing pair over approximating components. But in prior work, actually, pairs with self-references and pairs without self-references, there are incompatible types. So before and after escaping, the types actually change. So this has two undesirable results. First is that we need to do some term level coercion for escaping. So specifically in this example, you can see that we need to do some eta expanding, basically extracting components from an existing pair and reconstruct it using a different type signature. That's the first undesirable thing. And the second is that since the type signature is different, we need to use different specialized eliminators, basically component extractor functions before and after escaping. So this is really undesirable. So in this work, in order to fix such problems, we use some combined development on both the declarative side and the algorithmic side. We start with the top level algorithm. We need to do some kind of polarity-based avoidance that in some of the covariant cases, we replace variables with self-references, and in contravariant cases, we need to remove such ill occurrences of variables. And to prove such variable is actually a good way to do this, a sound way to do this, we need to have a spec. And this spec, for this spec, we develop type and qualifier subtyping, which is precisely what's missing from our prior work. And why didn't our prior work have such subtyping? Well, for some reasons. First of all, self-references in subtyping, they carry different semantics on both sides of the subtyping, because they denote to the outer qualifier respectively, and the outer qualifier can change in subtyping. So their semantics will also have to change, and that change will have to be covariantly. Secondly, while the covariant semantics of self-reference allows us to have self-references safely occurring in all covariant positions, for some of the use cases, especially when we are dealing with church-encoded data type structures, we still need the self-references to occur in certain of the contravariant positions. So in this work, we have some syntactic restriction to allow such negative occurrences in where covariance or contravariance doesn't really matter. You will find more details in our paper about this. The second challenge of our algorithmic design is about polymorphism. And yeah, so basically we need to find a qualifier to replace the bound variable when we are considering reachability polymorphism. So our solution here is that we develop a bidirectional typing algorithm that infers qualifiers from parameters. For bidirectional typing, we know, so that basically means that we need to have two modes. One mode is that we infer the types and qualifiers, and one mode is that we check the types and qualifiers. But for this work, for this specific goal, we need more. So the first newly added case is that we need a hybrid mode that checks the type but infers a qualifier. You can see this from the first example shown there. So we need to, when we are considering applying the identity function with a new variable x, we need to infer the parameter qualifier x on x by checking its type and infer the qualifier x, and then using that inferred qualifier for substitution. So this kind of polymorphism is what we call a lightweight polymorphism as an alternative to explicit quantification and instantiations. And to backing up this hybrid case that's checking the type and infers a qualifier, we also introduce a new algorithmic subtyping form that infers a super qualifier while checks the upper bound of the type. What's complicated about it is that the interesting cases can again be found on self-references. For example, in certain types of function applications, we will be coercing a type without self-references into a type with self-references. So by such a subtyping, we will be posing constraints on the self-reference of P. So more details can be found in our paper about how we define our unification for qualifiers, which is also inspired by the either instantiation approach for type polymorphism. So a quick recap, a quick sum up. Our development is fully mechanized in Lin 4, the proof assistant. Our mechanism is split in roughly two parts. The first part is about the derivative specification. We have combined type and qualifier subtyping, and we prove semantic type soundness about it. And for the algorithmic implementation, we build qualifier checking and inference algorithms. And on top of that, we also have algorithmic avoidance conversions carried out in an implicit way. And we prove soundness and decidability of our algorithm, that our algorithm designs terms in finitely many steps, and all accepted terms are valid with respect to our specification. For evaluation examples, we did several of them. Firstly, include church encodings of data structures and also primitive forms of pairs and lists. Also, we try to explore patterns of race-free parallelism and the safe use of capabilities, for example, scoped file programming. And also, we explore different kinds of reachability patterns, including escaping data structures, and also, for example, structures with separate components. For example, this M-list stuff, classic example you will see with separation logic, basically. So as for annotation burden, in most cases, we see that on these examples, qualifiers add less than 20% of the size, and these numbers should be even lower on larger examples. And also in terms of the performance of a type checking, the timings of our type checking algorithm on different examples fits a quadratic curve and scales expectedly. So before closing up, I want to recap a little bit about the landscape of research on reachability types. So the initial language design was proposed in 2021, and later on in 2024, polymorphism and freshness marker has been proposed to strengthen the language. The language has been leveraged to do effect reasoning. So there was a GraphIR compiler defined, there are equational series explored, and on Wednesday there was a talk that was also given by me on how to use that to do type state programming. And also there's parallel work on how to strengthen the store topological, for example, how to allow cycles to be expressed in stores. There's also one talk on Wednesday. But the emphasis of this work is that we want to build algorithms and implementations, and we want those algorithms and implementations to be sound and expressive enough for escaping data types, and those can provide guides to prototype designs. So to conclude, in this work, we are looking at expressive algorithmic reachability types. By expressiveness, there are several things we are looking at. First, we want to track resources in escaping data. Second, we want to automatically avoid ill-scoped variables from types. And thirdly, we want to support inference for reachability polymorphism. So in all of these cases, we can see that the concept of self-references is both a key mechanism and the main challenge. So our development goes into two folds: the declarative specification with subtyping that is expressive enough for conversions with respect to self-references, and we prove type soundness by logical relations. And for the algorithmic part, we devise checking and inference algorithms, we devise implicit avoidance conversions, and we extended the bidirectional typing mode to fit into the picture, basically. And our solutions proving sound and decidable, fully mechanized in Lin 4, and our artifact is available online. Thank you very much for coming, and I'm happy to take any questions.
So I would like to ask a little bit about the evaluation of annotation.
Yeah.
Right. I mean, not all annotations are necessarily equally difficult. So, right. Are there certain ones that you think developers might find more burdensome than others?
Yeah, good question. So, first of all, I should explain a little bit about how that percentage number calculated. So, that's you should think of it like number of tokens, like words we wrote. And for example, for a reachability annotation, sometimes it contains multiple variable names, so individually it contains different tokens. So that's how we calculated it. In that regard, I think 20% is not a great number. Secondly, I think definitely, as you hinted, there are some of the annotations that should be harder to figure out than some other annotations. I think this is especially true when we are considering higher order functions, because when higher order functions, we need to consider that which level is this resource being captured, and sometimes when we are taking in higher order functions as arguments, this is more a problem because we have to speculate what kind of functions we are receiving. So that would be the challenging case.
Questions from the audience?
Nice talk. I think this is works about the type algorithm, right?
Yeah.
So I'm curious that what is the I guess it's a type is probably need to have some approximation, and otherwise it's probably hard for user to use it. Otherwise, user need to write on very precise type. So is there the loss of user burden, or what happens if the user provide a not quite precise type? What happens?
Yeah, as with all type systems, the program is getting rejected. The user see a type error. They can have the chance of fixing that. Of course, I guess that I believe that's the nature of doing typed programming.
Is there any hints to the user which part is wrong?
Yeah, definitely. So basically, you can think of function applications as checks of coming in two forms, subsumption checks and separation checks. For both of the cases, we will be providing you, hey, there's one argument with a concrete variable name, which I think is true, that is appearing on the actual side, but not allowed on the expected side.
Okay, thank you.
Thank you.
Let's thank the speaker again.